right, one, two. Okay, there we go. Hello and welcome to lecture. Today we are going to finish off chapter 5. I'm sorry, I'm a few minutes late today. Sorry, I just said chapter 5. We're in chapter 6. We're finishing off chapter 6, starting chapter 7, assuming everything goes well. Okay, so we ended on talking about changes in heat and how changes in heat correlate to changes in temperature, and the key equation we are going to be using is Q equals MCAT, where Q is the amount of heat, of thermal energy, either being gained or lost. M is mass, C is specific heat capacity. We said that is the amount of energy it takes to heat 1 gram of a substance by 1 degree Celsius, and then delta T is change in temperature, which is final temperature minus initial. And we can use this equation to solve problems like the following. So I'm just going to give myself a little more room to work here. Alrighty, so we can solve problems like the following. Let's write this in black, not orange. 15.0 grams of water at 23 degrees Celsius experiences a change in energy that leaves the sample at 32 degrees Celsius. So there are 2 parts to this question. Part A is determine the amount of energy gained or lost is part 1 first. Also know that the specific heat capacity of water is 4.184 joules per gram degree Celsius. And then part B is, was this process exothermic or endothermic? All right. So first things first, let's start with part A. For part A, we are trying to find the amount of energy gained or lost. And that is another way of saying we're trying to find Q. All right, now let's look at what we're given. the first thing you should write down under your given information is anytime you're asked to find a quantity like Q that has an algebraic expression associated with it, you want to write down that algebraic expression under the given information because it will provide you a roadmap to solve the rest of the problem. So we're asked to find Q. Q is equal to M times C times delta T, right? Q equals MCAT. So to find Q, we need to find mass. We need to know mass, specific heat, and change in temperature. Now let's look at the quantities given. We are given a mass, right? We have 15.0 grams of water. We're given the specific heat capacity of water, which is 4.184 joules per gram degree C. But then we're given, what's interesting is we're given two temperatures. We're told that our initial temperature is 23 degrees Celsius and our final temperature is 32 degrees Celsius. Now, when you look at this equation, we're given mass, we're given C, but you may be wondering, okay, well, what temperature do we use for delta T? And the answer is neither. Delta T is the change in temperature. Whoops, sorry, to do this, there we go. Delta T is change in temperature. Change in temperature is equal to final minus initial. Anytime you have a change in that triangle symbol, delta, it equals final state minus initial state. So we actually have to calculate a value for delta T based on our initial and final temperature here. So when we do, see that delta T is equal to final temperature, 32 degrees Celsius, minus initial temperature, 23 degrees Celsius. And when you punch this into your calculator, you find that your change in temperature is, well, your calculator tells you it's 9, but you have to ask the question, how many sig figs should this answer have? And when you're doing subtraction, we have to look at the precision of each number, where the last significant digit of each number occurs. And for 32, the last significant digit is in the first decimal place. For 23, the last significant digit is in the, not the first decimal place, the first place, the ones place. You know, the hardest place value there is. And so our answer must have its last significant digit in the ones place, and 9 does. So our change in temperature is 9 degrees Celsius, and this number only has one significant figure. Now that we know our change in temperature, we can plug them all in to this equation and find our value for Q. So let's go ahead and do that now. Q equals MCAT. Our mass is 15.0 grams. Our specific heat is 4.184 rocks. Exactly, it is 9 degrees Celsius. Joules per gram degree C. Delta T, we just calculated, was 9 degrees Celsius. And that's it. We just got to multiply these numbers together. So I'm going to bust out my calculator because I can't do this in my head. 15 times 4.184 times 9 is, so my calculator is telling me that my value is 564.84. Now, when you look at how many sig figs our answer can have, our mass has 3 significant figures. Our specific heat capacity has 4 significant figures, and our change in temperature only has 1. So that's going to limit us. We round to 1 sig fig, 6 rounds up. So the correct answer after rounding to the correct number of sig figs is 600. And our units, you'll notice, grams cancel grams, degrees Celsius cancel degrees Celsius, and so the unit we have left over is joules. So 600 joules is the value for Q, and that is the answer to part A, 600 joules. Now let's talk about part B. Let's talk about whether or not we are endothermic or exothermic. I'm just going to write this in parentheses up here. All right. Endothermic or exothermic? Exothermic is a word that means energy is released totally. Rocks, the only reason why it's easy when I do it is because I've been doing these problems over and over again for well, let's see. Well, I first took college chemistry in, okay, this is going to date me, but 2005. So it's 2021. So it'll be 16 years ago this fall. And that was my first year of college, fresh out of high school. And soon after I declared chemistry major. I majored in chemistry in undergrad. Then I went to grad school for it. And then after I finished grad school, I started teaching. So literally for the past 16 years solid, I have done nothing but chemistry every single semester. No breaks. I didn't take any time off. It's just been semester after semester after semester. And here's the thing. If you do anything for 16 years straight, it's going to come natural. It's going to feel natural because you've just had so much repetition. You can do it without thinking. And the danger is, when you're watching me do problems, the danger is you see me do it, it looks easy, but then when you're on your own, you can trip up. And the best analogy I can think of is it's the difference between like when you have a 9-month-old, a 1-year-old, a baby who's just learning to walk for the first time. If they see a human being who's 16, they see someone who has been walking for 16 years, the baby is going to look at them and go, that looks effortless. But then when the baby takes its first step for the first time, they're like wiggly, they might fall. And so the key thing is to practice as many problems as you can that are different than these ones on your own so that you get the reps in. Because the thing is, whenever you take your first step, it's pretty much a guarantee that you're going to falter, that you're going to get stuck, that there's going to be a problem. And you don't want that to be on an exam. So you want to get reps in working problems on your own before you get to the test so that you have some practice and some familiarity with these problem types before you get there. So that would be my recommendation is for any topic, Google topic, Gen Chem worksheet. The internet will spill out a bunch of examples. You can find them, you can do them, and get as many reps in with these types of problems as you can. All right, so anyway, sorry, that's my little infomercial for independent problem solving. And then, sorry, one last thing, I'm not quite done. When you do get stuck, bring them to lab, bring them to office hours, and we can work through them together, and I can show you where you're getting stuck and how to break through. And that process of getting stuck, getting help, and breaking through the other side, then you grab the next problem. You get a little farther, but get stuck in a different place. You come get help, break through, break it to the other side. That is what cements this kind of stuff in your head. So that's really the best way to engage with this material. All right. Okay. Now my infomercial for studying is done. Exothermic, energy is being released. When energy is released, your value for Q will be negative. All right. Endothermic, by way of reminder, means that energy is absorbed. And when energy is absorbed, the value for Q is positive. So you can compare that to the value we calculated, which was a positive 600, right? So this reaction, this process, it's not a reaction, this process is endothermic because Q is positive. So you can look at Q to determine endothermic or exothermic. You can also look at your change in temperatures. If you started at 23 and you ended at 32, your temperature increased. That means your energy increased. You absorbed energy. If you started at a temperature and ended at a lower temperature, that's energy released, so that would be exothermic. So those are the two things you can look at. Either the sign of Q, whether it's positive or negative, or did your temperature go up? Then you absorbed energy. Did your temperature drop? You released energy. All right. Okay, so that is, well, we're going to do a couple more examples like this one because this is just one of those topics that is good to get repetition on. All right. Okay, so here, let's do another problem. All right. So a student is trying to determine the identity of an unknown metal. All right. Let's see. They're trying to determine the identity of an unknown metal. It is either copper that has a specific heat capacity of 0.39 joules per gram degree C. Lead with a specific heat capacity of, sorry, I can't quite see it in my notes. There we go, 0.160 joules per gram degree Celsius, or gold with a specific heat capacity of 0.129 joules per gram degree Celsius. They find that 0.500 kilograms of metal goes from 25 degrees Celsius to 44 degrees Celsius when it absorbs 1,225.5 joules of energy. Determine the metal's identity. All right. Now, you'll notice, first thing, right? We're trying to determine the metal's identity. And we're given three choices. We're given gold, gold, lead, or copper. And there's a key piece of information included with each possible identity, and that is the specific heat capacity. So basically, in other words, we need to find the specific heat capacity of the metal, right? Turns out, specific heat capacity is in this equation. So if we know our change in temperature, the amount of energy absorbed, and the mass of the metal, we can use this equation to solve for specific heat capacity. Let's look at what we're given. Turns out that we're given the mass of our metal. So there's check. We got the mass of our metal. We're also given the amount of energy that is absorbed. So check, we got Q. Now, for our change in temperature, you'll notice that we're not explicitly given. Oh wait, hang on. Were we given this at all? Oh, yes, we were. Okay, I was like, whoa, did I not give its temperature? I did. We're not explicitly given change in temperature. We're given initial temperature and final temperature. So we've got to calculate our delta T on our own, but we can, because we know change in temperature is equal to our final minus initial, and we do have both of these. So I'll put a tentative check there. That means we have enough information to solve for C. So let's take Q equals MCAT and divide both sides of our equation by mass and change in temperature. Mass cancels and delta T cancel. So we get a new expression. Our specific heat capacity is equal to the energy absorbed divided by the mass of the metal and the change in temperature that it undergoes. So real quick, let's, oh, hang on. I meant to do this in a different layer. Sorry, I know they got ugly for just a second. There we go. Okay. So let's calculate, as I was saying, our delta T. Final temperature was 44 degrees Celsius. Initial temperature was 25. Whoops. So our change in temperature has a value of 19. Sig figs wise, our last sig fig needs to be in the first or in the ones place, and it is, so we don't need a round. That's the value we can use for specific heat capacity, or sorry, for delta T. So we have an energy of 1,225.5 joules. We have a mass of 0.5. Where was it? There we go. 0.500 kilograms. And we have a change in temperature of 19 degrees Celsius. 1,225.5 divided by 0.5 divided by 19 is 129. And you'll notice that of these three choices, none of them are equal to 129. This might be disconcerting until you recognize that the mass that we plugged in was in kilograms, but the mass of each specific heat capacity given was in units of grams. So this is actually 129 joules over kilograms degrees C. So we need to convert our mass from kilograms to grams to get it into the same units so that we can appropriately compare our calculated specific heat capacity to those given. So let's do that unit conversion and then we'll recalculate. 0.500 kilograms. We need to convert from kilograms to grams. 1,000 grams are in 1 kilogram. Now, your calculator will tell you that the answer is 500. The problem is 500 only has one sig fig, and 0.5000 has 3. So we actually need to write our answer here in scientific notation. This would be 5.00 times 10 to the second grams, so that we have 3 sig figs preserved. All right, and now let's plug this in to our derived equation and see what we come up with. Sorry, we've already solved for specific heat capacity is equal to the energy absorbed over mass times delta T. We absorbed 1,225.5 joules of energy. We're dividing by 5.00 times 10 to the second grams times 19 degrees Celsius. Punching this into, wait, hang on, let's go. 1,225.5 divided by 500, right, because that's what 5 times 10 to the second is, divided by 19, comes out to be 0.129. When you look at how many sig figs our answer can have, we're limited to 2, and 9 is going to round up. So this will be equal to 0.13, and then our units are joules per gram degree Celsius. That is our specific heat capacity that now we need to use to identify the metal. Now, when you look at it, none of them are an exact match, but you'll notice that our 0.13 is really the same value as 0.129. It's just rounded to a different number of sig figs. So that tells us this is a match, because what 0.13 clearly isn't 0.39, clearly isn't 1.6. So the identity of our unknown metal is gold. All right, and that is that problem. All right, I have one more example using kind of calculating changes in energy, etc. That I want to do, and then we will move on straight into chapter 7. Oops. So this is the last example for chapter 6. 250 grams of iron at 34 degrees Celsius loses 1.20 kilojoules of energy. Determine the temperature after this loss. And the specific heat capacity of iron is 0.444 joules per gram degree C. All right. So, as with any problem that we're going to solve, we need to identify first what we are trying to find. And we're trying to determine the temperature after the loss of energy. In other words, we're trying to find our final temperature. Now let's talk about our givens. Can you think of any equation that has T2 in it? And in the context of the problems we've been solving, you can say, yeah, T2 is in the equation for delta T. Delta T is equal to T2 minus T1. We're trying to find T2. So if we can find delta T and T1, if we know delta T and T1, then we've got it made. Turns out we've been given our initial temperature. It's 34 degrees Celsius, right? It's right here. There's our T1. Let's see what else we are given. I'm trying to shift this up a little bit. All right, what else are we given? We're given the mass of our metal, 250 grams. We're given Q. It's 1.20 kilojoules. We're also given our specific heat capacity. It's 0.444 joules per gram degree Celsius. All right, now you'll notice we're given right out of the gate, we're given our initial temperature, but we do not know our change in temperature. Oops. We do not know our change in temperature. What are we given? Instead of change in temperature, we're given C, we're given Q, we're given M. That means that we are going to need to use Q equals MCAT to find that change in temperature, to find that delta T. If we if we divide both sides by mass times specific heat capacity, we can isolate delta T. Delta T is equal to the energy absorbed or lost, in this case it's lost, over mass times specific heat capacity. We know all three of these values, and so we're good to plug in. Now, delta T equal to 1.20 kilojoules over mass 250 grams times specific heat capacity, 0.444 joules per gram degree C. I've made two mistakes here. I've made two mistakes on purpose. I've deliberately done it because these are two mistakes that I see over and over on the exam, and I want you to learn them before you take it. So here are the two mistakes I made. One of them you've seen already. One of them you haven't. The first one that you have seen is, you'll notice that my energy units are in kilojoules, but my specific heat capacity units are in joules. These will not cancel. So I need to do a conversion before I crunch my numbers. All right, you've seen that mistake before. I did it in the previous problem, but again, it's super common and I want you to avoid it. The second mistake I've made is with Q. Specifically, the fact that this metal has lost 1.20 kilojoules of energy. When you have a loss of energy, that means that Q, the value for Q, is a negative number. And if you plug in a positive value for Q, you will not get the correct answer. Because Q is not a positive number, we've lost energy. So Q does not equal 120 or 1.20 kilojoules of energy. It equals negative 1.20 kilojoules of energy. All right, so that is the second mistake I made. So we need to do a quick unit conversion, and we need to make sure we're plugging in a negative value. Otherwise, our answer will be far off. Okay, so first step, let's take negative 1.2 kilojoules and convert this thing to joules. 1 kilojoule has 1,000 joules in it. Kilojoules cancel. So this is -1, or punch this into your calculator. Comes out to be -1,200. Again, the problem. This number only has 2 sig figs, whereas we started with 3, so we need to end with 3. So after the conversion, it'll be -1.20 times 10 to the third joules. Now let's plug this value in. To our equation. and get the correct value. All right, so negative 1.20 times 10 to the third joules. That is the amount of energy lost. You'll notice that our energy units cancel. Our mass units also cancel. Temperature is the only thing that's left, which is what we want. And so now we're good to punch our numbers. So negative 1,200 divided by 250 divided by 0.444 gives us a delta T that is equal to negative 10.81081108. We can keep 3 significant digits. Oh, nope, I take that back. Our mass only has 2 significant digits, so we can only keep 1, 2. This 8 is going to round up. So our delta T, our change in temperature, is negative 11 degrees Celsius. Don't let the negative sign freeze you out. That's a horrible pun, made completely accidentally. Don't let the negative sign freak you out. That's what I was trying to say. Because a negative change in temperature just means that the temperature decreased. That's a totally normal thing. We experience it all the time. So don't worry if your delta T has a negative value. It's totally normal. Now, we've done a lot of work. It would be very, very easy at this moment in time to just box this and go, sweet, done. But we weren't asked to find delta T. We needed to know delta T so we could find T2. So we still have a little more algebra ahead of us. All right, so let's take a look. Delta T is equal to T2 minus T1. To get T2 isolated on one side of this equation, we need to add our initial temperature to both sides. They'll cancel there, negative T1, positive T1 equals 0. So our final temperature is equal to our change in temperature plus our initial temperature. Now our change in temperature was negative 11 degrees Celsius, and our initial temperature was 34 degrees Celsius. You punch that into your calculator. Your calculator will tell you that 34 minus 11 is 23. Sig figs wise, last sig fig needs to be in the ones place. This one has its last sig fig in the ones place. And our units are degrees Celsius. So this is T2, our final answer. Our final temperature was 23 degrees Celsius. All right. These problems are particularly, they can be very challenging for some students. They're very involved. A lot going on. And they go by the name, these problems are generally called calorimetry. Calorimetry problems. So if you Google calorimetry worksheets, PDF, they're very common in chemistry classes. The internet is full of practice worksheets, and I can personally guarantee, because I've done them each and every one myself, that they're all excellent. So if you need more practice on this, hit up Google Calorimetry Worksheet PDF. You're going to get a ton of options to get good at this type of problem, which will definitely show up on exam 3 and the final as well. All right. That brings us to the end of chapter 6. and we are now officially diving into Chapter 7. Let me just pull up my notes. No. Yes. Chapter 7. Okay. Yes. Okay, sorry. So in chapter 6, we were talking about all different phases of matter. Spend a lot of time on the gas phase, but we're talking about phases of matter in general. And there was one type of phase that we didn't really hit. And you may be wondering, what do you mean? When we talked about phases, we talked about the gas phase, right? We talked about the liquid phase. We talked about the solid phase. What else is there? And some of the kids in the class might be going, it's plasma. Plasma is a phase. We're not going to talk about it in this class. There's another phase that is more relevant to day-to-day life, more relevant to introductory chemistry. That's why I'm talking about it. And that is this phase. AQ is the aqueous phase. And the aqueous phase, when something's in the aqueous phase, that means that compound, that chemical, is dissolved in water. All right, dissolved in water. That's what it means to be in the aqueous phase. So the aqueous phase shares a lot in common with the liquid phase because it's literally something, a substance, that's been dissolved in water. So it's in the liquid phase. Now, we're going to talk about not just the aqueous phase, but we're going to talk about this in a that's what I'm looking for, a little bit more broadly than that. Not even just things that are dissolved in water, but the what we're going to focus on in this new chapter is the solution phase. All right, that is going to be our focus here. And the aqueous phase is a solution, but it's not the only type of solution. So we're going to be looking at things from a wider angle. So this begins our discussion of solution chemistry. This is a topic that is very near and dear to my heart. Every single reaction that I ran in graduate school was done in the solution phase. So without this, I would have never had a degree. All right. Now, before we dive into solutions, specifically, I want to talk more broadly about mixtures. All right, mixtures. Now, mixtures come... whoops. Hang on. There we go. So mixtures come in two there are two, can be classified. Let's try that again. Mixtures can be classified into two broad categories. And those categories are homogeneous and heterogeneous mixtures. All right. A homogeneous mixture is a mixture in which there is an even distribution of all components of the mixture. Oops. Oh, snap. Hang on. Okay, okay, hang on. Sorry, this is going to look weird for just a second. I don't know how Photoshop did this, but I started writing in my background layer. It's going to take me just a hot second to fix it. No. There we go. Okay. Well, that was an easier fix than I was afraid of it being. All right. Sorry for that strange interlude, but we're back. Okay, so there we go. All this because I realized I misspelled components. So in a homogeneous mixture, you have an even distribution of all components of the mixture. All right. So an example of this would be like cream in coffee. Right, once you pour cream into coffee and you stir it in, there's an even distribution of cream and coffee, right? There's no portion of the cup that has more cream or less cream. Once you stir it, it is a homogeneous mixture, even distribution throughout. A heterogeneous mixture involves an uneven distribution. An uneven distribution of the mixture's components. Now, an example of this would be water and sand. If you scoop into a cup on the beach some ocean water and sand. You've got the ocean water, but all the sand is kind of on the bottom. There's still water in it, right? It's wet sand. Water's still down there, but it isn't the same. There's a lot less sand up top. There's a lot more sand down below, and vice versa with water. And that is an example of a heterogeneous mixture. Now, solutions are homogeneous mixtures of solutes and solvents. All right, that is what a solution is. A solution is a type of homogeneous mixture, and we're going to dive into that now. All right. So, we're doing a chapter on solution chemistry. Let's start by talking about what a solution is. I'm going to, just so you know, use this shorthand for the remainder of this chapter and course. I'm going to write solution like this. If you're wondering why, it's because the way my calculus teacher wrote solution. He would just do that, and I got used to doing it in his class when I took it 15 years ago. Still stuck with me. All right, so let's, so anyways, when I write that, that's my shorthand for solution. If you are looking for a definition for solution, a solution is something dissolved in something else. All right, a solution is something dissolved in something else. And the something that gets dissolved, this is called a solute. And the something else that dissolves the solute is called the solvent. All right? It is, so a solution then is a solute dissolved in a solvent. All right, so it's a solute dissolved in a solvent. That is the definition of a solution. We more or less have an intuitive sense for what a solution is. Like I said earlier, cream in coffee is a solution. But I want to take a moment and maybe expand the application of these concepts to regions where we're not used to thinking of solutions. Because when I say the word solution, you think wet automatically, and it's not always the case. So there are two different phases of matter can be solvents. All right? There are two phases of matter that can serve as solvents. You're like, whoa, I thought it was liquid. Well, it is. That's one of the two, but there's another one that can also be a solvent, and that is the gas phase. So a gas can be a solvent, and a liquid can be a solvent. Now, it turns out that not all solvents can dissolve all solutes. So, for example, a gaseous solvent can only dissolve gaseous solutes. So a gas can only dissolve other gases. A gas cannot dissolve a liquid. A gas cannot dissolve a solid. So though a gas can be a solvent, the only type of solute it can dissolve are other gases. And you might be going, that's weird. But you're breathing a solution of gases right now. When you think about our atmosphere is 78% nitrogen. It's got about, what, like 22% oxygen, smaller percentages of carbon dioxide, water, vapor, a gas, and argon. And those other gases, argon, CO2, water vapor, oxygen, are solutes, solute gases dissolved in the solvent gas of N2, of nitrogen. So, I don't know, talking about the atmosphere always makes me like very conscious of my breathing. I don't know why. That and watching Demon Slayer makes me very conscious of my breathing. I'm like, water wheel, second form. Sorry, I don't know all the forms. I'm sure there are anime humans who know all 10 water forms, or lightning forms, or beast forms. I like the self-taught. Anyways, we're not going to start talking about anime right now. Let's keep it on topic. Gas. If you have a gas solvent, it can only dissolve gaseous solutes. Liquid solvents, on the other hand, can dissolve gaseous solutes, liquid solutes, and solid solutes. So if you are a liquid solvent, you can theoretically dissolve all three. An example of a gaseous solute in a liquid solvent would be carbon dioxide in LaCroix. Right, when you crack open a can of LaCroix today, product placement, peach pear. Actually, just kidding, I'm not sponsored by LaCroix, though that would be awesome. I totally welcome it. I would drink him on every single stream. If someone in the Midwest hears this, I'm totally down. I'll even show you how refreshing it is at room temperature. All right. Nothing like a room temperature LaCroix. When you hear the bubbles coming out, fizzing, I don't know if the mic's probably not picking that up. That is gas, a gaseous solute escaping the liquid solvent of the water. Another example of a gaseous solute in a liquid solvent would be oxygen in water. So I used to think when I was a kid that, you know how like fish breathe through their underwater with their gills? I was like, well, water is H2O, so there's oxygen in water. I used to think that a fish's gills was stripping that oxygen out of the water molecule and using it to breathe. That is not what's going on. A gill is actually a filter, a superfine filter that catches when the fish pushes water through the gills, it catches the dissolved O2 gas from the atmosphere in the water, pulls it out of solution, uses it to breathe. So it's actually a fish, all fish are breathing O2 gas that has been dissolved in water. It's O2 that's in the aqueous phase. It's another reason why, I don't know if you've ever seen a fish suffocating, if a pond gets very, very low and it hasn't been replenished with water, a larger volume, when the water level gets very, very low and it's overpopulated, there's too many fish that are filtering the oxygen gas out of the water, they're breathing it faster than oxygen can get from the atmosphere back into the water, and so they can start suffocating because the lake has been deoxygenated by overpopulated fish, or overpopulation in fish, I guess I should say. If you want to watch some very sad, desperate videos, Google fish asphyxiating or fish overpopulated pools or whatever. They like start like wobbling and like dying, and then they're rotting. And anyways, it's very bleak and morbid. Go watch a video of it. Those are two examples of a gaseous solute in a liquid solvent. What about a liquid solute in a liquid solvent? That one's kind of weird, but it's not as weird as you think it is. This is cream in coffee. You're pouring one liquid, cream, into another liquid, coffee. The one is the solute, the other is the solvent. This is also ethanol in vodka. Ethanol is a liquid. Water is a liquid. When you dissolve ethanol in water, that's what all liquors are, not just vodka, but whiskey, tequila, whatever your poison of choice is. Now, you might be wondering, but Josh, if we're mixing a liquid with a liquid, which one is the solute, which one's the solvent? I'm so glad you asked. The solvent is the one that there's more of. Whichever one is in the minority, that is the solute that gets dissolved in the bigger whole. And the funny thing is, most brands of vodka are 40% ethanol by volume. And so that means they're 40% ethanol, 60% water. So ethanol is the solute, water is the solvent. But if you've ever purchased or consumed Everclear, that thing is 90% ethanol by volume. So in a bottle of Everclear, which is 90% ethanol, 10% water, you're actually not drinking ethanol and water anymore. You're drinking a little bit of water dissolved in ethanol. So the role of solvent and solute changes depending upon which one there's more of when we're talking about two liquids. All right, finally, for solids, sodium chloride in water, right? That's salt water. Sugar in coffee. There's another solid solute in a liquid solvent. That one's probably the most intuitive of the batch. All right, now, so that's kind of a introduction. When we say solutes and solvents, most of us are familiar with it on some level, but our minds usually go straight to liquids and solids. Turns out gases can be solutes and solvents. Liquids can dissolve gases. Liquids can dissolve liquids, in addition to liquids dissolving solids. So it's a broader category than we're used to thinking about, based on the intuition we get from our day-to-day lives. Yep, Rox, that is exactly it. Spot on. Okay, so that's kind of our introduction to solutes and solvents. Now, once we start talking about solubility, solubility is concerned with the amount of solute that can be dissolved in an amount of solvent. All right. So, for example, solubilities will vary depending upon the identity of the solute and the identity of the solvent. Different solvents have different solubilities for the same solute. Different solutes have different solubilities in the same solvent. For example, sodium chloride is very water soluble. All right, sodium chloride is very water soluble. So, for example, 1 gram of water can dissolve 0.36 grams of sodium chloride. All right, that's like a third of its weight. If you have a mass of water, it can hold an extra third of its weight just in sodium chloride. That is high solubility. In contrast, silver chloride, you'll notice we have the same anion here. It's silver chloride. It's chloride both times, but we've just changed it from sodium to silver. Silver chloride is very insoluble in water. By contrast, so 1 gram of water can dissolve, let's see, I had to write this down, 0.0000002 grams of silver chloride. The solubility of silver chloride is so low that silver chloride is considered insoluble. Oops. In water. All right, so these are two examples of the wide range of solubility that you find. With sodium chloride, water can dissolve a third of its weight of sodium chloride in itself. All right, that's how much it can hold. Whereas silver chloride, water can hold 0.002% of its weight in silver chloride. All right, it's a very drastic difference, which is why compounds like silver chloride, whose solubilities are that low, we just consider them insoluble because it's like almost nothing is in there. It's so small, it's negligible. One thing that's worth pointing out before we leave the topic of solubility is temperature influences solubility. All right, temperature influences solubility in two ways. First, solid solutes become more soluble at higher temperatures. All right, solid solutes become more soluble at higher temperatures. I should say in liquid solvents. Whereas gaseous solutes become more soluble at lower temperatures. In liquid solvents. So temperature affects solubility, but it affects it opposite for gases and liquids. All right, or sorry, for gases and solids. The reason why solids become more soluble at higher temperatures is, when you think about it, the liquid phase is higher energy than the solid phase, right? The liquid phase is higher in energy than the solid phase. And so a higher temperature, a hotter liquid is able to give that energy to the solid and it's able to pull it up into solution. So the more energy that's there, it can give that energy to the solid solute, dissolve more in solution. And the same reasoning explains the phenomenon we see in the gas phase. The gas phase, or sorry, I'm going to start with the liquid both times. The liquid phase is lower energy than the gas phase. And so because the gas phase is higher in energy, if this liquid is cold, the lack of energy helps pull more gas down out of the gas phase into the liquid phase. This is why, for example, if you leave your carbonated beverage of choice out at room temperature, it's going to go flat, because when it's in the fridge, it's cold, it's able to keep the bubbles trapped in there. But as it warms up, the gas becomes less and less soluble and escapes into the atmosphere. So, decrease in energy helps the solubility of gaseous solutes and liquids. Increase in energy helps the solubility of liquid solutes in solutions. The other thing that can affect gases, this doesn't apply to liquids, is, I should say, gases are more soluble sorry about that. In liquids under high pressure. All right, so that's another reason why when you open a can, you hear that gas escaping. They're stored under higher pressure, so more of it will stay in solution before you start drinking it. All right, and that's where I'm going to pause today. We'll pick up on Thursday, talking about saturated and unsaturated and supersaturated solutions. Again, office hours tonight. Lab tonight is just office hours. Stop by if you have any questions. We can talk about all of it. Later, dudes.